Section: Introduction. In this section, we present a detailed evaluation of the Reka models, core, flash, edge, on language and vision tasks. We also discuss their development, benchmark design, and training pipeline. The Reka Edge and Flash models are dense, with 7B and 21B parameters, respectively. Our evaluation demonstrates that these models are cutting edge for their computational class, often outperforming much larger models. The current version of Reka Core competes with top models in both automated base model evaluations and blind third-party human evaluations. We compare the Reka models with large language models, LLM, APIs based on price and performance, using the MMLU score as an indicator of model quality. All Reka models are positioned on or beyond the Pareto frontier. Reka Core performs comparably to GPT-4v on various evaluations and surpasses all Claude 3 models on multimodal chat human evaluation. On video question answering, both Reka Flash and Core outperform Gemini Ultra. In language benchmarks, Reka Core achieves competitive scores compared to other leading models. In text-only chat, Reka Core outperforms GPT-4 and ranks third on our internal leaderboard. The Edge model surpasses state-of-the-art models in its class, outperforming Gemma 7b and Mistral 7b. The Flash model also outperforms larger models such as Grok 1, Mistral Medium, and Gemini Pro 1.0. In multimodal evaluations, Flash outperforms Claude 3 models and matches the Sonnet model on certain tasks. Overall, the Edge and Flash models are powerful in their computational class. Additionally, we provide insights into the technical details and training processes of these models. The training data consists of a mix of publicly available and proprietary datasets up to November 2023, including text, images, videos, and audio clips. Reka Flash and Edge were trained on extensive language tokens, with a significant portion related to code, STEM, web crawl, and math. A portion of the data is deliberately multilingual, covering 32 languages, with additional training on the multilingual Wikipedia. The multimodal training data includes images, videos, documents, and web pages, carefully selected for quality and diversity. The architecture of our models involves a modular encoder-decoder structure for processing various inputs. The backbone transformer model is based on the GNOME architecture, incorporating SWI-GLUE, grouped query attention, rotary positional embeddings, and RMS norm. Reka Flash and Edge use a sentence-piece vocab of 100K based on the GPT-4 tokenizer. Pre-training involves a curriculum with different mixture distributions, context lengths, and objectives. The models are trained with BFLOAT16. Section Summary. In this section, we provide a detailed overview of the Reka models, Core, Flash, Edge, and their performance on language and vision tasks, showcasing their state-of-the-art capabilities within their respective compute classes. Our evaluations demonstrate that Reka Core competes with leading models like GPT-4 and outperforms models like Claude 3, while Reka Flash and Edge surpass models such as Gemini Ultra and Gemma 7b, showcasing their power within their compute class. Additionally, we discuss the training data, which includes a mix of publicly available and proprietary datasets, with Reka Flash and Edge trained on trillions of language tokens, and the architecture details, highlighting the modular encoder-decoder structure and key components like the transformer model and specialized vocabulary. Section: Context length. In this section, we discuss our standard model's context length, which is 8K for regular models. For Reka Flash and Reka Core, we have a longer context length of 128K for tasks involving retrieval and long documents. All our models perform well in needle in the haystack tests for the context they handle. Based on our tests, it seems that our 128K models can effectively handle a context length of 256K, but not beyond that. When training with long contexts, we not only use instruction tuning data but also create additional supervised fine-tuning data synthetically. This is done by conditioning on long documents from our pre-training corpus using a method called reverse instruction tuning from long documents. Our Reka models were mainly trained on NVIDIA H100s using PyTorch. Our setup includes clusters from various vendors, with a peak compute power of around 2.5K H100s and 2.5K A100s. We have a total of 6 clusters, and more than 90% of our compute resources were available by mid-December 2023. Reka Flash and Edge were trained using hundreds of H100s over several weeks. Despite using very aggressive learning rates, our pre-training process was smooth with minimal loss spikes, even for larger models. We utilized the Ceph file system to enhance the I/O performance of our clusters, especially for scalable training with multimodal inputs, although this came with additional maintenance tasks. We have observed significant unreliability in GPU nodes, often due to hardware errors or connectivity issues. The reliability of providers also varies greatly. We have reported the average number of node failures across 4 providers in table. Node failures are influenced by the number of nodes used concurrently for training, leading to different estimated failure rates for various configurations. Apart from differences across clusters and providers, there can also be high variance over time periods. For instance, clusters may behave differently during the initial weeks of handover or after significant changes. The early phase of handing over a cluster or introducing new nodes can lead to a chaotic period lasting days or weeks. The active usage of a cluster for distributed training by previous customers plays a key role in the difference between the early chaotic phase and the stabilized phase. We have developed a custom inference stack for text and multimodal tasks running on a mix of A10s and A100s. Kubernetes serves as the orchestration engine, managing large clusters across different regions. After pre-training, our models undergo instruction tuning for multiple epochs with strong regularization. We use a mix of datasets for this, including proprietary and publicly available data. Subsequently, the models are aligned with RLHF, specifically PPO, using the same family of Reka models as the reward model. Our models undergo multiple rounds of RLHF. Additionally, our post-training process involves considerations beyond the scope of this report, such as tool use, function calling, and web search. We collect data using external companies and provide them with a user interface for annotating text-only and multimodal data. Our annotation software supports individual point-wise quality annotation, side-by-side evaluations, images, videos, text-only prompts and responses, as well as multi-turn dialogues. In terms of evaluation, we conduct extensive assessments of our Reka models, including language-only and multimodal evaluations. For language models, we compare performance across various evaluations such as general language understanding, reasoning, arithmetic, code generation, and graduate-level question answering. Section Summary. In this section, we primarily focus on the context length of our models, where our regular models have a context length of 8K, while Reka Flash and Reka Core utilize 128K for long context models. We conduct needle-in-the-haystack tests to evaluate the performance of our models, with the 128K models showing potential extrapolation to a 256K context length. Additionally, we discuss our training process, compute infrastructure, hardware challenges, phases of stability, inference setup, post-training procedures, and evaluation metrics for our Reka models. Section: Multimodal, Image, Video, Evaluation. In this section, we compare our models using various visual question answering datasets such as MMMU, VQAV2, and Perception Test for video question answering. We focus on Reka models, specifically looking at their performance in a zero-shot setting. Our results show that Reka Core competes well with other advanced models. It performs similarly to GPT-4 in most metrics, falls between Opus and Sonnet from the Claude 3 series, and has mixed outcomes when compared to Gemini models. We also conduct a blind evaluation of our chat models with human raters from a third-party data provider. We evaluate 2 setups: multimodal chat, where users ask questions about images, and text-only chat. Human raters are given prompts and model-generated answers to rate based on provided guidelines. We use ELO scores to compare model performances, considering only strong preferences expressed by annotators. Our evaluation dataset covers a wide range of prompts. In the multimodal chat evaluation, Reka Core outperforms most models significantly, with Reka Flash following closely. In the text-only chat evaluation, Reka Core competes well, outperforming some models like Claude 3 Sonnet and being surpassed only by a few others like GPT-4 Turbo. Reka Flash also shows strong performance, surpassing models like GPT 3.5 Turbo and Gemini Pro. We utilize Reka Core's capabilities for model development and automatic evaluation, particularly in the context of multimodal chat. By simulating human judgment and comparing model outputs to reference answers, we can assess model performance effectively. Despite some differences in rankings between Reka Core and human evaluations, overall, Reka Core provides a good approximation of final outcomes. Furthermore, we conduct cross-lingual evaluations on various multilingual benchmarks, comparing our models with others like Llama 270B, GPT 3.5, and GPT-4. Reka Core consistently outperforms baseline models on most tasks, showing strong performance across different benchmarks. It outperforms GPT-4 on tasks like XCOPA, XQAD, and Tidaka, while also surpassing Flash on all benchmarks. Overall, Reka Core proves to be a reliable performer in multilingual settings. Section Summary. In this section, we evaluate our models using visual question answering datasets such as MMMU, VQAV2, and Perception Test for video question answering, with all results being zero-shot for Reka models. Comparisons show that Reka Core competes well with other frontier-class models, performing similarly to GPT-4 in most metrics and falling between Opus and Sonnet from the Claude 3 series. Additionally, in multimodal chat evaluations, Reka Core outperforms various models significantly, except GPT-4v, while in text-only chat evaluations, it ranks competitively, surpassing models like Claude 3 Sonnet and GPT-4, and being surpassed only by GPT-4 Turbo and Claude 3 Opus. Section. Long Context Question Answering. In this section, we conducted a series of evaluations on long context question answering. We used internal benchmarks in two domains: movie plots and twos, terms of service, contracts with contexts around 100K tokens. Both datasets involved question answering tasks where we had to answer questions based on a long document. We compared our Flash and Core models with the latest Claude 3 models and found that both Flash and Core were competitive. Next, we compared our Reka models with state-of-the-art domain-specific medical models like Metatron and MedPalm2, as well as GPT-4. We evaluated our models on three benchmarks: MedMCQA, PubMedQA, and MMLU, Medical. Our results showed that Reka Core performed well against these specialized medical models. Specifically, Reka Flash and Core outperformed Metatron, Reka Core outperformed MedPalm2 and GPT-4 on MedMCQA, and Reka Core slightly lagged behind GPT-4 on MMLU, Medical. On average, Reka Core outperformed MedPalm2 and performed similarly to GPT-4 on medical tasks. We then provided detailed comparisons of Reka Edge and Flash against other models in a similar compute class. Reka Edge showed strong performance against other 7B models like Llama 2, Mistral, and Gemma, outperforming them on all benchmarks except for math. On the other hand, Reka Flash was compared with larger models like Llama 270B, Gemini Pro 1.0, Mistral Medium, and Grok 1. Despite being smaller, Flash either outperformed or was competitive with these larger models on most benchmarks.